All right, let's talk about the materials of the future. We're not just talking about your everyday steel and iron. No. We're on a quest for the super materials, the stuff that's engineered for the most extreme jobs you can possibly imagine. So let's dive in.
So why can't we just use metal for everything? I mean, it's a great question, right? Metals are strong, they're versatile, we've been using them for thousands of years. But here's the thing. As our technology keeps getting more and more advanced, we're really starting to push the envelope. We need materials that can go places and do things where metal, well, it just can't keep up.
And this is exactly where metal starts to fall short. Think about the insane blistering heat inside a jet engine, or trying to make something perfectly transparent. Or how about building for aerospace, where every single gram counts? Yeah, for jobs that need this kind of wild mix of properties, we need something totally different.
Okay, so if not metal, then what? Well, our first stop might surprise you. We're talking about ceramics. Now, I know what you're probably thinking. Pottery, bricks, that sort of thing, right? And hey, you're not wrong, but that is just scratching the surface of what these materials can do.
So what is a ceramic really? At its most basic, it's just a compound made of metallic and non-metallic elements. The name itself comes from the Old Greek word for potter's clay, which gives you a hint about its ancient history. But trust me, what we can do with ceramics today is a whole different ballgame.
This really lays it out perfectly. You've got your traditional ceramics on one side, the stuff we've known for centuries. But then on the other side, you've got these high-tech industrial ceramics. So what's the big difference? It all comes down to control. We're talking about engineering them at a microscopic level, getting the purity just right to create materials that can do some seriously amazing things, like in aerospace or even medical implants. And check this out. This is a fantastic example. We are not talking about your grandma's teapot here. This is a high-tech hip replacement. And those smooth white parts? That's ceramic, a mix of zirconia and alumina. Why? Because it's unbelievably hard and it just doesn't wear down. It's exactly what you want for a joint that needs to last a lifetime inside your body.
And just how hard are we talking? Well, to put that into perspective, you've probably seen those super sharp ceramic kitchen knives, right? The material they're made of, zirconium oxide, scores an 8.2 on the Mohs hardness scale. For comparison, hardened steel is way down at a 6. Diamond, the top of the scale, is a 10. So it's getting up there. That's why those knives stay ridiculously sharp for so long.
But wait, it's not just about being hard. Take a look at these ball bearings. They're made of silicon nitride, another advanced ceramic. First off, they're 40% lighter than steel ones, which is a huge deal. But get this, they can handle temperatures up to 1400 degrees Celsius. That's insane! So you've got lightweight, super hard, and crazy heat resistance. That's the trifecta for any kind of high-speed, high-performance machine.
All right, let's shift gears to our next super material, and this is one you definitely see every day. Glass. Now, the real magic of glass isn't what it's made of, but how its atoms are put together. See, in a metal, the atoms are all lined up in a nice, neat, orderly crystal grid. But glass? Its atoms are a total mess, all jumbled up. It's almost like a liquid that's been flash frozen in place.
Okay, so we all know what glass is like, right? You drop it, it shatters into a million pieces. In its normal form, like a window or a drinking glass, it's famous for being weak and brittle. And that's because the surface is covered in these teensy tiny microscopic flaws, and each one of those is like a little engraved invitation for a crack to start.
So that brings us to a really interesting puzzle. If glass is so famously weak, how on earth can it also be stronger than steel? It sounds impossible, right? But the secret isn't in its chemistry, it's all about its form.
Take a look at that number, 7 gigapascals. That is the potential tensile strength of a single, flawless glass fiber. And yeah, that is way stronger than a lot of high-strength steels. It turns out the incredible strength was in the glass all along, it was just being hidden by all those tiny little flaws on the surface.
So how do we unlock all that hidden strength? You melt the glass and draw it out into these incredibly fine fibers. When you do that, you get rid of most of those surface flaws. And that's what we know as fiberglass. You weave those strong fibers into a mat, mix them with plastic, and boom, you get the strong, lightweight composites we use in everything from boats and cars to tennis rackets. Okay, for our last stop, we're looking at maybe the most versatile element of them all, carbon. This stuff is the ultimate shapeshifter. Just by changing how you arrange the atoms, you can get one of the softest materials known to man. And you can also get the absolute hardest. Same element, totally different results. And this just lays it out so clearly. On one side, you've got graphite. Think pencil lead. Here, the carbon atoms are in these flat sheets that can just slide right over each other. That's why it's so soft and works as a lubricant. But then you look at the other side, and you have diamond. It's the exact same carbon atoms, but now they're locked together in this super rigid three-dimensional structure. And that's what creates the hardest substance on Earth.
Okay, now follow me on this because this is really cool. You start with that graphite, with all its layers. Now imagine you could just peel off one single layer, just one atom thick. What you'd have is something called graphene, and in that one sheet, you unleash all the incredible strength of those carbon bonds. Now, take that one atom thick sheet and roll it up into a tiny, perfect tube. That is a carbon nanotube. It's got all that amazing strength, but now in a brand new structure.
And that idea of building things at such a tiny scale, well, that takes us to our final frontier, the world of nano. We're talking about the future of materials, where we're not just mixing things in a big vat anymore. We are designing and building things one atom at a time.
To really wrap your head around this, we have to think on a totally different scale. So forget inches or millimeters, we're talking about the nanometer. This is the world where scientists are literally picking and placing individual atoms exactly where they want them to go.
Just how small is a nanometer? Okay, picture a single strand of human hair. A nanometer is about 100,000 times thinner than that. It's almost impossible to really imagine. But yeah, at that scale, you're basically playing with Legos, except your Legos are individual atoms. And when you can control matter with that kind of precision, you can start to create materials with properties that sound like they're straight out of science fiction. You get rid of all those tiny imperfections that make things weak. This leads to things like pure computer chips, lighter and stronger bike frames, and even ceramics that you can bend and cut like metal. The applications are revolutionary, touching everything from medicine and sensors to batteries and solar cells.
I mean, just get a load of this potential. Remember those carbon nanotubes we were just talking about? Some of them, in theory, can carry 1,000 times more electricity than copper or silver. Let that sink in for a second. 1,000 times. That one single property could completely revolutionize, well, everything, from the tiniest electronic device all the way up to our entire power grid.
So when you really step back and look at the big picture, it's pretty mind-blowing, isn't it? Our journey with materials started with our ancestors shaping clay into pots. And today, we're arranging individual atoms to design matter from the ground up. We've gone from shaping mud to basically programming matter itself. And that leaves us with one huge, exciting question. What on earth will we build next?